Hi guys, welcome to the second episode in my coding challenge series. My name is Idowu Akinde. Again, as I said in the first episode, my goal with this series is to take us, by us, I mean current students and recent graduates of computer science, through practical, demonstrable, everyday programming steps to solve many of the popular coding challenges that are available on the internet. To this purpose, in the last episode, we picked the popular Mars rover challenge and we solved it together on screen real time. This time around, we are picking the equally popular Fizz Buzz challenge and we'll solve it together. If you look at the screen, you will see the problem description. All right, so without much further ado, let's get cracking. So again, like I always say, half the programming task is the problem solving. I've been on the interviewing side of a few hundred programming interviews, and I can say that my interest is always significantly raised whenever I see a candidate who pays more attention to the logic and the thought process that goes into solving the stated problem, rather than the candidates who dive head first into the problem and try to start to code.
It's 6 o'clock.
So what am I saying? I'm saying in order to solve this challenge, whatever the challenge is, any type of challenge, you do well to, first of all, think through that challenge and try to solve it. Try to break it down, first of all, rather than diving headlong into programming just yet. In this video, we will use the popular unit testing as a component of test-driven development. So we will address some of the aspects of test-driven development today, but more importantly, we will be focusing on the unit testing aspects of test-driven development. Red, green, refactor, arrange, act, assert, essentially building features from a test-first perspective. So we'll do that in a few moments. Let's just fire up our Visual Studio and kick it off from there. Visual Studio, where art thou? Is that a RAM problem? Okay. All right. I'm waiting for Visual Studio to load so that as I'm explaining my thought process in breaking down this problem statement, I will be doing it into a file, just like a template file within Visual Studio, just to be clear about that. So let's create a new project. Okay, let's create a .NET Core console application. Okay, all right, let's call it Fizz. I have 3 Z's there. Fizz Buzz. Should we call it Fizz Buzz or Fizz Buzzer? Fizz Buzz, Fizz Buzz, Fizz Buzz, Fizz Buzz. All right, we'll come back to that in a moment. Locate it in this special folder. Okay. Create a brand new folder for that project, and please go ahead. All right. Okay. Okay. So before we go too deep into that, this is the reason why I opened up Visual Studio, so that I can do this. I can put up my comments in this place. Okay. All right. All right. Problem statement says print a. 1 second, please. All right. It's a rather simple statement, but you'd be surprised what it will reveal to you concerning the thought process of candidates when you throw it at people that claim to have 8, 10, 12, 15 years of programming experience. I particularly like the Fizz Buzz challenge because it helps reveal the thought process of many programmers, many so-called programmers. Okay, so the program statement says write a program that prints the numbers from 1 to 0. That sounds like the simplest thing ever, right? If it's a multiple of 3, it should print Fizz. If it's a multiple of 5, it should print Buzz. And if it's a multiple of 3 and 5, it should print Fizz Buzz. Very simple, infinitely simpler than the last challenge that we did, the Mars Rover challenge. Okay, so again, like we did in that exercise, again, we are going to be looking out when we are reading the natural language of the problem. We're going to be looking out, or reading the natural language of the problem, we're going to be looking out for pointers to expected behavior from our program. So in this case, it's kind of explicit. Write a program that prints the numbers, okay? Print numbers 1 to 100. That's a behavior. That's an expected behavior, right? Okay. Another expected behavior is now, if it's a multiple of 3, it should print Fizz. Okay, so if we come here, print Fizz, and then I can put in bracket and say when multiple of 3, right? I can say that, okay? I can say equally for the second condition, if it's a multiple of 5, it should print Buzz. Print Buzz when multiple of 5. And in this for this third condition, if it's a multiple of 3 and 5, it should print Buzz. So I can say here, print Fizz Buzz. Fizz Buzz when it's a multiple of 3 and 5. I know you can see what I'm typing, but that's because it's behind. So that's it. So we're good. Behind 3 and 5. Okay. All right. So this pretty much is the exhaustive list of behaviors that is expected from our system. Now, again, because I said that we're going to use this opportunity to demonstrate unit testing and its practical application in everyday programming. Before I got, raptured and signed up to the TDD movement, I would have created a class right now and started to create methods and started to create, loop structures, whatever those may be, that would address this expected behavior. However, we're going to go through the proper process of doing unit testing. And first of all, and what that means is that we're going to build, first of all, tests and then matching functionality in our main class that satisfies those tests. If you think about what I'm saying, what that means is that we are going to create expected behaviors and then validate those expected behaviors in our class structure or in our design, in our coding design. What it also means is that the process of using TDD and unit testing usually helps you as a developer to extract out from your problem statements those major pieces of expected functionality as unit tests, okay? So essentially, your list of expected behaviors, aka list of tests, is a simplified, streamlined, bare bones set of technical or functional requirements, that you can use to validate what you're going to build later on. So right now we have this close to natural language. We also have this. We can close that gentleman now, and then we'll refer to it as the time goes by. All right. So we have a project here. We have a console application here that prints, hello world. We necessarily do not need this, so let's rename that to. Rather than rename, let's add a new class, and then we'll take out the program.cs, because that's usually its first thing. Add a new file, and when it gives us the prompt, we'll add a class, and we'll call it Fizz Buzz. Okay, so our namespace is Fizz Buzz. Our action class is Fizz Buzz. Okay, new. All right, thank you. All right, so what this therefore means is that, okay, so we have that. What this means, okay, so we can take this out. All right, so the first thing we will do, so that's like scaffolding. So certain TDD purists might say that, oh, ID, you started to create code even before your first failing test. But essentially, I haven't written any code. All I've done is just done some scaffolding. So technically speaking, if I run this thing now, I haven't implemented anything. So let's go to Fizz Buzz. Let's go to the project. The solution rather, and add a new project, which will be our test project. Add new project. Okay. And then if we go to .NET Core and tests, I like XUnit because it is the predecessor of all the other NUnit, MSTest, JUnit, PyUnit, and so on and so forth. So let's just do that, and then let's call this Fizz Buzz Test. I like the plural because this is the project name, okay? So I usually do that. Solution name, Fizz Buzz, and so on and so forth. Okay, so in this unit test now, I'm going to rename this gentleman to Fizz Buzzer should. Uh-oh. What happened? I must have touched something on the keyboard. Fizz Buzzer should. Okay. I'll explain the should nomenclature later on. And then each of my test methods will have a grammatically consistent verb that matches this Fizz Buzzer should. So I'll say Fizz Buzzer should. Our first requirement in that place is to print numbers 1 to 100. Fizz Buzzer should print 1 to 100. Okay, and that's that. Okay. In this place, I'm going to make this fail. Now, one thing in practice, over time, you will learn to skip what I'm about to do, but just to demonstrate the process for new people, for people that are new to test-driven development and unit testing, I'm going to do something called assert dot. Ooh, I don't have assert dot pass. Okay. All right. So I'm just going to say assert dot true 1 equals 1. Okay. Replace with true. Okay. So that's fine. Simpler the better. Assert dot true true. All right. Okay. So And if I want to have a first failing, so what I'm doing with this is that I'm demonstrating to you guys that are new to this that the test framework is working, okay? And so if I go to my view and test, that will come up here under this guy. So let's move this gentleman somewhere here. If I do this, and I said run all tests, obviously this would come out true. And what does that do for me? It demonstrates, please hold on. Okay, so we can see the status update for that guy over there. It demonstrates that building. This, ideally, we should have something here under successful test saying one test passed. What that does is that it demonstrates to us that our test framework is working properly, okay? All right, so it's running the tests and it should pass any moment from now. Okay, Fizz Buzz, successful. So if I take this out, successful tests, Fizz Buzz. First of all, everything is green because I have only one test and it's fine. Fizz Buzz test, the unit test 1, the print 200, print 1 to 100, and that's fine. All right. I know the expected behavior from print 1 to 100 is to print something from 1 to 100, but not just yet. Okay. All right. So in order to then have my first red-green refactor cycle, I will then change this to false and run the test again. Okay, that's going to demonstrate to me on the, it's like the scientific method where you have a null hypothesis and an alternate hypothesis. That's exactly what we're doing here. So we had a set of conditions that we ran the first time and the test passed. We then we did the logical inverse of that set of conditions and changed true to false and expect it to fail. And indeed, it has failed. Okay, so let me enable all these guys back and we have that. So, so we have our test framework set up properly. We've achieved two things now. We know that our test framework is working fine. We also know that we have our initial failing test, which is what we have right now. Okay, so we need to move on to the green phase. Now, what are we trying to do here? We want to be able to, we're trying to express through this test that if someone were to test an application that we will write, which we haven't written but we will write, that person will be expecting to probably run a method or perform an action, and that action will print all numbers from 1 to 100. So we will then say something like, now this is where the AAA principle, the arrange, act, assert principle comes to play. So assert naturally falls under assert, and then the second one is act, and the first one is arrange. So here we have where we set up our objects. So ideally, what would happen here is that we would have something like, type Fizz buzzer. Okay, so as you can see, we are not able to access the other library because I want to write Fizz buzzer. I want to write Fizz buzzer dot some kind of method name. I want to refer to this other method, to this class, the Fizz buzzer class. So from this test, I need to go to dependencies and add a reference, project Fizz Buzz, and okay. And then I can say using Fizz Buzz, I can say using Fizz, what did I just add? Yeah, I just added Fizz Buzz. Come on. Oh, so we have different namespaces. All right, so that's fine. Under here we have, what do we have here? Namespace is Fizz Buzz. Okay. So ideally, this namespace should be this, so that when we do this, we can say, oops. And then we can say Fizz Buzz dot Fizz Buzzer dot. Now I can create a fictional method name that I know doesn't exist, but I will satisfy the requirement for it in a few moments. So I can say Fizz Buzzer dot print normal. Okay, if I define normal, or just to be more explicit, let's say print 1 to 100. Okay, and it doesn't need any parameters. Okay. Oops, that's my act. All right, let me cut that out. Okay, so under arrange is where I initialize variables. So I was trying to create here Fizz Buzzer, a class for the Fizz Buzzer object. I could call it Fizz Buzzer, and I'll equate that to a new Fizz Buzzer. Okay. Now, so that does that for me. Okay, that creates the object. Under the act, I would then refer to Mr. Fizz Buzzer, okay, and call that method that I just print 1 to 100. Okay. Now, obviously, this method does not exist. Okay, and we all know that. So I know that if I were to run this test right now, it will build, and it will come up with an error that says that this method does not exist. One error, 0 ones. Okay. What that does is that it then helps me to identify that I'm still in my red phase. How do I move to green? Visual Studio, like I always say, the best editor, the best code editor, the best IDE in the world, gives me the facility to do a quick fix and automatically generate a method that satisfies this condition. So with what I just did, I can go back to my Fizz Buzzer class, and I'll see a brand new method in here that has this exception. Okay, so now this satisfies my condition, and it will throw this new exception. Okay. Build successful, run is giving us a fail. Why is it failing? This time around, you see that the failure description has changed from a Boolean true or false to system of not implemented exception, which is what we specified in, well, what Visual Studio automatically specified for us. Okay, all right. So another way to be more explicit with this is to say that because ideally this kind of, the output of this method, print 1 to 100, is ideally a multi-line. If you have a console application, 100 lines with an integer each on each one. In order to test that, it may be a bit cumbersome. So what I would suggest that one can do, one way to address that is to create a Boolean variable that says that if this is successful, then go ahead and set that Boolean variable to true. If not, leave it at false. So in addition to this variable here, I can declare a Boolean and call that Fizz Buzzer state and equate it to false. Okay, and say that Fizz Buzzer state equals that. Okay. This should be capital B and capital S. All right. Okay. Okay. And then what this means, let me see if Visual Studio, the best ID in the world, has any. Okay, so it doesn't have anything. So let's go there and change the return type of this to string that. Okay. And then in here, it is what it is. Okay. Cannot implicitly convert to bool. Oh, why did I change that to string? What was I thinking? All right. So that's that. All right. Da, da, da. So if we run it again, we expect to have this same not implemented exception. But we can, somewhere in here, we can deliberately force it to green by saying, excuse me. So here, we're saying Fizz buzzer state, assert that Fizz buzzer, we know that Fizz buzzer is still false. Assert that Fizz buzzer, true that Fizz buzzer state equals true, because we know that it's still false, okay? Because we didn't change the variable there. So let's go. Okay, so there we go. Inspect our failure again, and we still have the not implemented. All right. As you can see now, what we've done is that we've made this constructor, it's just a default constructor. So you see why I said earlier on that effectively I hadn't added any new code. I just created scaffold. In fact, this constructor is what enables us to be able to create a new object here. Right. So assert true, Fizz buzzer state equals true. All right. Public class unit test 1. And we have all of these guys available for that. So what we have done right now, excuse me, what we have done is that we have established that we can create a unit test in the red phase. We can create a unit test in the red phase. We can convert it to the green phase by modifying code. And then we can start to improve on the code that is executed in that function to establish it. So let's go one step further and actually get some output for this print 1 to 100. So if we come here, we can namespace Fizz Buzz, okay, Fizz Buzz. Print numbers 1 to 100. Console.writeLine. Okay, so in here, we can do a for loop that checks I between 1 and less than or equal to 100, and I between 1 and 100, and then I++, and then does console.writeLine I. Okay. Sure. All right. So now, the throw new not implemented exception was overriding the compiler's default, type checking for our method. Right now, it's because we don't have that default exception type being thrown, we need to provide a return value. I usually have this rule of thumb that whenever I have to return something, I declare that return variable at the beginning. So here I'll say bool ret, and then return ret. This helps me never actually forget to return a return value. Okay, so the onus is then on me, just like the arrange actor set. The onus is then on me to make sure that I process whatever needs to be returned. So I would then say that reps equals, if I'm sure that this is fine, then I can say that reps equals true, and that's that. So I would then say that this is this. I expect to have a passing test now when I go back to my Fizz Buzzer show. So Fizz Buzzer is that, Boolean is that, Fizz Buzzer state equals that. Now, if I set the true that Fizz Buzzer state equals to true, just to accept. Now, because I know that I returned a true here, I want it to fail first, so I will deliberately change this to false. Okay? Deliberately change that to false, just so that I can get a true-false exception in this unit test. Let's wait for that and see how it pans. Are we done? Yes, we are. If we inspect the reason for the failure, for the failing test, we see that it's because of a Boolean mismatch. The expecting true actually is false. If I go back here and then set this to true and run it again, run all tests again, I will see that I have a successful method that prints all 1 to 100. Okay, so I have a green here, and that's fine. Okay, so in my requirement specification, I can say that I have met this requirement, this evolutionary step in my solution development. I've satisfied this condition. Okay, so if we mark conditions that we've satisfied with those 3 asterisks, we've satisfied the first one. Now, how do you, so if someone wanted to validate some random, say we built this in 2019 like we're doing now, and in 2024 someone were to pick up this piece of code, and the person is under no obligation to accept our claims that indeed we have built something that can print numbers 1 to 100. That person has a right to dispute our claim. How can that person validate that our claims are true? The person can validate by coming to this method and running this method. And if the person gets a true status, then all is well. Okay. If we also go to our, because we did a console statement here, if we go to our, no, that's a package console. If we go to our console, we will also have where do you see that? We'll come back to that. Come back to that. Where's that console? How do you get the console? We'll come back to that. Okay. So print all numbers. There has to be toolbox properties, document outline, errors, tasks, results, device log, interactive. No, that's not the package console. That's not what I want. I want the immediate window to see the output of my console.writeLine. Okay. So just to establish that, I would deliberately, I want to trigger the behavior of the console. So I'll deliberately just do this. Okay, so we have it over there. So there it is. Looking for the terminal. Uh, so this is where pair programming helps. Move this out of the way. Breakpoints, locals, watch. Okay, hello world. So there we are. So instead of this, I want to have my, I want to run this gentleman. So if I come here and I say, Fizz Buzzer, so the same thing I did here, instead of doing this, can you define an object, a Fizz Buzzer object for me? Okay, new Fizz Buzzer. Boolean Fizz Buzzer state is false. Do I even need that? I don't need all of that. I can just execute it. All right. I should be fine like that. So if I were to run this again, I should have the expected output come. Ooh. Okay, so there we are. 1 all the way to 100. Okay, so we have that. Thank you. This is the previous one. Just memory management. Let's close that. All right, so we have this on Fizz Buzz. Fizz Buzzer print 1 to 100. And that validates that what we're doing is actually working. So now, the next behavior that we want to validate is to print Fizz when it's a multiple of 3. So if we go back to our tests framework, we forgot to rename this. So we already renamed it here, but we forgot to rename it in the class. Okay, so that should have been that a long time ago. In X units, test methods are called facts. Okay, so over here, we can just say, this time around, instead of print 1 to 100, we want to print multiples of 3. Okay, and that's our test method. Okay, again, we'll create a Fizz Buzzer object. We define it to that, but this time around, the method that we're calling is a different method. So our fictional method may be print Fizz for multiples of 3. That looks like it's like a very long method name. So we'll just do this, and then we'll say accept the true blah 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 all over again. Again, it gives us that error. If we run it now, we'll build, but we'll throw that error, which is red. All right. So without much further ado, let's just generate the method for that. And like we did with the previous method, we have a brand new method here. If we run it now, we will have a not implemented exception. That's the red phase for our second method. Come on. So print 100 is fine, but print multiples of 3 is not fine. So not implemented method. So let's quickly implement what it will take to make that guy pass. So there's a principle in unit testing and TDD called the minimum effort principle. So at any point in time where you're moving from the red phase to the green phase, you're writing the minimum amount of code that is required to convert your test from a red fail to a green pass. In this case, we have a boilerplate code that we can get from the previous one. We will just need to put in some logic to check for whether that number, the current iteration of the number, is visible or not. Is divisible by 3 or not? Okay, so if we say print Fizz for multiples of 3, Again, running through the loop 1 to 100, console.write line. First of all, we don't want to write that just yet. So we say console.write line I plus 1, but just before we write, are we not trying to determine whether the current value of I is I divisible, a multiple, not divisible, a multiple of 3 or not? Okay? So if if I is a multiple of 3, what should it do? Okay? Is I a multiple of 3? So we have our if. Okay? So if I, now, depending on the language you're using, the modulo operator varies per language, but this is the most popular implementation of the modulo operator across the languages, the percent sign. So if we say that I% 3 equals 0, if this is equal to 0, yes, I is a multiple of 3, then write console.write line Fizz. Okay, since we have a pattern, or policy, whatever you want to call it, of oops, let me just follow the standard. Okay, I was trying to run ahead of the interpreter. Okay, else console.write line. Oops. Come on. The fingers are a little twitchy today. I wonder why. All right, so what this does is that if we have a multiple of 3, it will write Fizz. And if we don't have a multiple of 3, it will not write anything. Okay, so for instance, let's say that we forgot to implement this. What do we expect? We expect to see a multiple of 3. So we expect to see blank line for 1 blank, 2 blank, 3 Fizz, 4 blank, 5 blank, 6 Fizz, 7 blank, 8 blank, 9 Fizz, and so on and so forth. So let's try that just to validate that we're running through an evolutionary way of building software. Right. So okay. So our tests are passing, and if we our tests are passing, if we then run this gentleman and take focus to our console window, hmm, 1 to 100, so something is wrong. We may need to debug to find out what's going on. All right, of course, we know what's going on. So we're still running the exact same code. We've made a change to the middle layer, to the functionality that actually prints multiples of 3, but we haven't made a change to the interface layer, the class that controls the console window. Okay, so over here we have to then come here and say, please run this method instead of the previous method. So copy and paste. Now we're fine. Okay, so evolution 1 was that we were able to print, or let me not be too optimistic that we will pass. Let me wait for the evidence before commenting on the result. Okay. Okay, so what this means is that 1, if we say that this is 1, 2, so if you divide 100 by 3, you would have 33 numbers. So instead of 100 numbers, you can see that we have about, obviously we don't have up to 100 instances of Fizz here, just about 33. So if you come here, just to make it more obvious, if you come here and you say, first of all, write I plus the dot, and then plus concatenated to that, just to give us exactly what we're doing. Just to be consistent, we may choose to do this as well. Okay. So that way it will be clear to everybody the specific number between 1 and 100 that Fizz was printed for. Come on, not now. Oh, you've been downloading. Oh, okay, we'll restart and install later on. All right. Console write line, da 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 da. Okay, so just like I said, 3, we didn't get anything for 1 and 2. 3, we got a Fizz, 6 Fizz, and so on and so forth. Another way to make it more, so this is what I was saying earlier, that was a result of having commented this out. We would then have to do this and that. So if we do this time around, it will be very obvious to everyone exactly what is going on. Okay, so this is the first one, Fizz, Fizz, Fizz. Okay, so 1, 2, Fizz, 4, 5, Fizz, 7, 8, Fizz, 10, 11, Fizz, 13, 14, Fizz, 15, 16, 17, Fizz, and so on and so forth. Okay, second evolution in our, so first evolution in this solution was that we had Fizz. It didn't look very meaningful, but it was accurate. It was correct, but it wasn't as meaningful as the last one. We went one step in meaning by showing the specific iteration number for each instance of Fizz. And then over here, we deliberately outputted something. We deliberately printed something to the screen for each instance where the condition of Fizz was not met. So for all of these guys, we can close. All right. All right. So we're good. We're good. We're good. All right. So that satisfies our second condition, second iteration in our problem solution, evolutionary solution development. Okay. The next one is that we want to do a similar check, but this time around, instead of checking for 3, we're checking for 5. And so our test method, we'll start from our test method and create a similar method for, rather than checking for 3, we're now checking for 5s, for multiples of 5. So over here, we will assume that there is a method called that. Just because we've done it so many times, we can just go ahead, generate that method. It will give us a not implemented exception. We will, it was a not implemented exception. We will run it, and we will have 3 methods, 2 passing and 1 failing. Okay, so there we are. There's our test results. Okay. System not implemented. We should be familiar with that now. So if we basically just duplicate this. And change for specificity. So over here, instead of checking for multiple of 3, we're checking for multiple of 5. So if it's instead of Fizz, do me a Buzz. And if we change our interface manipulation class, or interface output class, whatever you want to call that, if we first of all do a unit test, we should pass this time around because we've changed the implementation from throwing just a random exception to actually performing valid actions. Thank you very much. So we have valid passing tests, and then what about behavior? Let's see what our behavior looks like in the console. Okay. So this time around, we had for 1 to 100, we had our Fizz. 1 to 100, we have our buzzes. Okay, so as you can see here, with all of these lines from 1 to 100, 1, 1, 2, 2, 3, 4 buzz, 6, 7, 8, 9 buzz, 11, 12, 13, 14 buzz, 15, 16, 17 buzz. Essentially, when the number ends with a 5 or a 0, you see a buzz. So those are the multiples of 5. Okay. Again, evolutionary step 3, satisfied. Who's noticing that as we advance, the earlier steps are where you do much of the work. As we advance, because you have a test harness that you can copy and paste, the work actually gets easier and faster. Also because you've established the thought process for validating your failures and turning them into passes, the work also becomes easier. Now, the last one is a bit tricky, but it's just a modification of what we've done. This time around, we're going to be checking for a multiple of 3 and 5. And when that happens, when there is a coincidence between 3 and 5, oops, I wrote 3 and 5 and 5. When there's a coincidence of that a number is both a multiple of 3 and at the same time a multiple of 5, then it should print Fizz Buzz. So, so I'm going to, so the description of this is slightly tricky. What if I did this? Print, now look at this statement, this behavior statement versus this one that I'm about to write. So you say print Fizz for 3 multiples, Buzz for, let's be grammatically correct, and Fizz Buzz. For multiples of 3 and 5, okay? I think that this second description fits this better. Because if we do this, we'll end up with a method that will just print out Fizz or Fizz Buzz for numbers like 15 that are both 15, 30 that are both multiples of 3 and 5, you know, and so on and so forth. And the other ones will just be printed normally, which doesn't actually satisfy our problem statement. When it's 3, so let's just get there. So let's get there. Let's print this first. Print Fizz Buzz when it's a multiple of 3 and 5. So if we go back to our test method and create a fact, or again, like in generic terms, a test method for it, we have multiples of 3 and 5. Okay, so over here, Fizz Buzzer, when multiples of 3 and 5. It will throw up a compiler error. We know, it will tell it to generate a method. And when we go here, we see our generated method with a not implemented exception automatically done for us. Okay, we will deliberately do a run all, and we expect to have a new failing test. Essentially, 4, excuse me, essentially 4 tests where 3 of them are passing and 1 of them is failing. So system not implemented exception, that's quite straightforward. So everything going on according to expectation. So let's do this now and start to convert our latest red test to a green test. Public bool. Okay, so let's run through this quickly. Multiple of 3 and 5. Okay, is a multiple of 3 and 5. And then instead of Fizz, we would have Fizz and Buzz. Now, in previous instances of this thing that I've done, it's usually Fizz Buzz as one word, but I saw this earlier on when I was interpreting this problem statement, that is, there's a space between Fizz and Buzz. So that's fine. If that's what the problem says, excuse me, then that's what we will do. So that's Fizz Buzz, okay? So this looks good, 3 and 5, what am I missing? 3 and 5, oh, there you go. So we have the condition here needs to be dual. So we need to have, so let's do the 3 first before the 5, okay? Control C, Command C rather, and that, okay? And then we can turn this to a 3. I modulo 3 and I modulo 5 at the same time, then give me a Fizz Buzz. I know now what I'm doing, what I've just done, this implementation satisfies this first description, behavior description, and I know, but I'm going to go ahead and run my method anyway. Command C, Command V. Test, get a green, and then run. Green, thank you. And then let's see our console. The console is getting large. We have a lot of tabs. All right, 100, 100, oh, those are previous instances. Okay, so you see what I was saying here. So 1, 2, 3, 4, 5, all the way to 14. We didn't see, like we did here, where we saw 1, 2, 3, 4, blah, 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 you know, 1 to 4, and then a buzz. This time around, we didn't see anything because it's checking for both conditions. So that is this implementation, and that satisfies this, that behavior that we just saw in our console satisfies Fizz Buzz. But this is the distinction I was trying to make. Fizz for multiples of 3, Buzz for multiples of 5, and then Fizz Buzz for multiples of 3 and 5. So what that means is that in our implementation method, we're going to have to step through, we're going to have to include logic that actually satisfies those earlier conditions. Luckily, we already have this method. So somewhere in the method that prints for multiples of 3, we know that if we check for this, this conditions helps us get the desired behavior. So we can come in here and we can do this. Okay, so I think this is actually redundant. Okay, if I modulo 3 is a 0, then print Fizz. If it's a 3 and 5, then print 5. I know that it will, I know, but I want to go through it. So if this were a personal project, I would go ahead and implement for the multiples of 3, right? Include code for the multiples of 5 and finish it up. But because I'm doing something, you know, like a tutorial, and I want you guys to follow along, I'm deliberately going through baby steps. So if you see what happened here, we have 1, 2 Fizz, 3, 4, 5 Fizz, 6, 7, 8 Fizz. You know, so it's checking, it's satisfying 3. Anytime you see Fizz, 3 was satisfied. Anytime you see Fizz Buzz, 3 and 5 were satisfied, but we're missing the 5, which I knew was missing, but I just wanted to validate that what we're doing is correct. So I would then go into the method that implements 5, get me these lines of code. And do this. If I3 is 0, give me a fizz. I5 is 0, give me a buzz. I3 and I5. So I could say this, okay? Else if, just to have consistency of logic. If I3 and I5, then give me fizz and buzz. And this should be the end, the final method that satisfies our condition. If, you know, I haven't missed anything out. So there you go, 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 go. Come on, come on, come on. All right. So 1, 2 fizz, 4 buzz fizz. Ooh. So we have, okay, so
it's 7 o'clock.
Can you inspect this behavior and tell me what's going on? So if you look at what's going on, the fizz buzz never appears. You know why? Because the fizz buzz condition is never run. And why is it never run? Because by the time we're using else if, so by the time the control pointer gets to something that would have passed for a 3 and 5, it would have passed for either a 3 earlier or a 5 earlier. So how do you fix that? Move this piece of code out of here and to the top. Okay, of course you can start with an else if. So else moves here. So it would be more logically consistent to check first for whether that iteration number is a multiple of 3 and 5 at the same time. Establish that, print your fizz buzz, and then for the rest of the numbers, anyone that's a multiple of 3, get it out. Anyone that's a multiple of 5, get it out. All right, let's test this. Oh, okay. So there we are. Okay, does this look correct? You tell me. 1, 1, 2, 2, 3 fizz, 4, 4, 5 buzz, 6 fizz, 7, 8 fizz, buzz. Fizz is a multiple of 3, 9 is a multiple of 3 fizz, 10 is a multiple of 5 buzz, 12 is a multiple of 3 fizz, 15 is a multiple of 3 and 5 fizz buzz. So, ladies and gentlemen, I think that we have satisfied this condition. Thank you for your time today. Thank you for being a part of this episode. I look forward to seeing you in the next episode. All right. I'm just trying to show all of these. I'm trying to keep all of these guys alive so that we can see the evolution of our solution. We started with fizz alone. We moved to buzz. And then we moved to buzz alone, and then we moved to fizz buzz alone, and then we moved to a version of fizz buzz that was inaccurate, and then another one that was inaccurate that didn't have fizz buzz at all. This other one had fizz and fizz buzz. Buzz was missing. This one had fizz separately, buzz, but no fizz buzz. And this gentleman satisfies our requirements. Thank you very much. Two things that I'd like to say. Now, we've demonstrated the red-green refactor cycle of unit testing and test-driven development. We've demonstrated the arrange, act, assert process for writing unit tests. We've also written I'm deliberately using this word, we've written inelegant code that meets our requirements. I said that deliberately, I use that word deliberately, inelegant. So is this the best, the most elegant, most optimal, most efficient code that we can write to satisfy these requirements? Absolutely not, okay? However, the practice of TDD and unit testing helps you arrive, using the growth mindset, to arrive at a solution through baby steps. So what you're doing is that you're not relying on superstar heroic abilities. You're pushing yourself little by little, bit by bit, until you build a solution. Unit testing is so powerful because of this principle I just mentioned, the ability to iteratively improve. And like we have finished this video now, and I have said that this is not the most elegant set of code or piece of code that can solve this solution. Over time, perhaps in the future, we might come back to this. I don't know, I'm not a prophet, but perhaps to demonstrate another principle in the future. Now that's the refactor, that's part of the refactor stage of the red-green refactor cycle, the continuous refactoring and improvement of your code. Of course, there's repetitive code. Okay, so if you look at this, all of this I3 and I5 code here is repeated in, it appears in multiples of 3 and 5, and it also appears in, so it doesn't appear anywhere else. That's unique because we're in 3 and 5. But the code that handles these 3 lines for multiples of 3 also appears here, and it also appears there. This satisfies our code, and not just to elongate this video too long, we can stop here. That can be your own mental exercise to try and clean up this code. You can send me your code snippets, send them as archives, zip archives, and I can inspect and give you feedback. But essentially what I'm trying to say is the challenge of improving your code is a lifelong challenge. So does test-driven development help you produce elegant code the first time around? Absolutely not. But will it help you produce the most elegant code, the most elegant code in a sustainable manner? Yes, it will. How? Because every time you make a change to that piece of code and you run it again and you run your unit tests again, you will be sure that you have not broken any functionality, because your tests will either continue to pass or start to break, start to fail. So that's the first thing I wanted to say. The other thing I wanted to say that I wanted to mention is about extensibility. So this problem statement described just 3 conditions: multiples of 3, multiples of 5, multiples of 3 and 5. What if after satisfying this, your customer then said, oh, my competitor is able to process multiples of 7 and multiples of 11. Dear development partner, can you make me at par with my competitor? Of course, you better be able to, otherwise you're out of business. So is this code extensible? Of course it is. How? Come here, define your new method that says print multiples of 3, 5, and 7, or 3, 5, 7, and 11. Define the scaffolding for the method. Create your stub method with the floating not included exception. Come here, refactor that method, and go ahead and satisfy the 7 condition. Go ahead and satisfy the 11 condition. Go ahead and satisfy the 13 condition. Whatever it is that you want to satisfy. This approach, this evolutionary growth mindset compatible approach to software development is probably the most powerful principle, or the most powerful thing one of the most powerful things that you will ever learn. On this note, I'd like to hang it here. Thank you very much. It's been about 1 hour and 10 minutes that we've been here. Thank you very much for your time today. I do appreciate your audience and your time. Again, if you have anyone that is in school that is learning computer programming, and perhaps sometimes feel that there's a disconnect between the lecture content and the industry practice, that is what this series is out to close. I'm out to close that gap. I'd like a future where the next time I'm interviewing current students on internship and or recent graduates of computer science and or aspiring software development professionals who may have any background, I would love to see them be at par, or at least be conversant with the industry practices. TDD, we will do TDD, we will do the solid principles, we will do the OOP principles, we will do DDD, domain-driven development, we will do BDD, behavior-driven, FDD, feature-driven development. We'll take up many of these topics over the coming episodes. So once again, thank you very much. Bye.